Okay, I say we've reached a quorum, both online and here in the room. There's about equal numbers of people in both categories. Delighted to see everybody. Delighted to have Dr. Eliah.F. Sabbas here to give a seminar today. She's on an extended visit from Brazil. She works at INPE, the equivalent of NASA Goddard Space Flight Center in Brazil. She's a senior civil servant there. As you're going to see today, she's interested in one of the more unusual aspects of our field, the interface of the Earth's atmosphere and its ionosphere, magnetosphere. She's interested in unusual phenomena, TLEs, sprites, jets, things like that, very visual, very optical things. She was actually here about a month ago, but in between, she's been installing an instrument in New Mexico, which it's a good topic to ask her a question. Where did she go? Why did she put it there? What is it for? What does it do? Of her big array in South America, a multinational array of optical instruments in South America has just made a leap into the United States. She's been on many student thesis committees and supervised numerous students. But I think, as you'll see, the most interesting thing is just how energetic and dynamic she is. And I believe this talk will demonstrate an achiever, a person who gets things done. And so with that, I hand it over to you.
Thank you, David, for the flattering introduction and the stimulus. And the subject that I study, as David was saying, it deals with the coupling of all the layers of our atmosphere, the neutral layers, and also the ionized region. So I like to see this as a big system, an integrated system, and it was very nice to be able to participate yesterday at the ISTP conference, where people were really discussing the heliophysics as a single integrated system. To my knowledge, this is the newest component showing all this integration and this coupling. So we have an image here of a group of sprites. So they do have these nice colors. This was observed from the International Station many years ago. You also see in this image, this is the nighttime, a nighttime lit viewing of the Earth. You see the light reflection of thunderstorm electric activity in the atmosphere. And we see here the air glow layer for a comparison. So the sprites, they can go from about 30 kilometers altitude up to 100, 105 kilometers altitude, piercing through the ionosphere. So they were the first to be discovered. And after that, we saw many other phenomena of this type, which are plasma. So they are hybrid plasma between the atmosphere and space. Everything starts at the sun. Good, my slide changed. With the energy coming from the sun, this is what gives life to our planet. This is what drives our planet. So the sun is our source. And as this energy comes to our planet, towards its path to the ground, it creates all the interesting regions that we in space physics like to study. The magnetosphere, the radiation belts, the ionosphere, and it also creates conductivity in our neutral atmosphere. When this energy reaches the surface of the planet, it starts to go back to space, being reflected as electromagnetic radiation. That's the first thing. And then it creates other structures. It creates thunderstorms, which are clouds that have electrical activity. And with that electrical activity, many phenomena happen that have signaled to us. We only discovered this, and when I say we, I mean us as human beings, only discovered these phenomena about 30 years ago. but they've been there since ever. It's just our capability to observe and to understand our planet is evolving with time. They show this coupling very clearly. The first aspect of the coupling that has been known, I think, since the 60s, is the global atmospheric electric circuit that I showed there. So here we have a representation of the lower levels of our neutral atmosphere, the ionosphere, and then the magnetosphere, and the whole system in the planet is coupled electrically. There is a very large potential difference between the ionosphere and the ground, estimated about 250 kilovolts. And this potential difference is, it creates an electric field that points towards the ground. So anywhere we go in the planet, there is a vertical electric field that's about 100 to 300 volts per meter. So my legs are about 1 meter high. So in this height, we have 100 to 300 volts potential difference. So this field is there even if there are no clouds. So how is it maintained? Well, it's maintained by all the thunderstorms around the world. So here we have a representation of thunderstorms. They work as an electric battery. Their charge is modeled as a negative charge center in the bottom and a positive on the top. Of course, their charge structure is much more complicated than that, but that's our simplification. I had a professor when I was an undergraduate who said something that I never forgot. We physicists model chaos by a sphere. So that's the way we do to create very simple ways to understand the system. So we model thunderstorm charges by two charge centers, just like as a battery. And they keep this field and this current flowing through the ionosphere and through the magnetosphere. So this has been well known. The new component of the system are the FAIRIES, which are a result of lightning activity. So when we have lightning, we remove a lot of charge from the cloud, and that creates an imbalance that creates fields from the cloud tops to the ionosphere. And one of the things that they can create are ELFs. The ELFs are a direct interaction of an electromagnetic when the lightning channel is closed, is complete, so complete connection between the cloud and the ground, or from the ground to the cloud. This can radiate an electromagnetic pulse. When it reaches the bottom of the ionosphere, it interacts and it creates extra ionization, it creates heating, and it creates optical emissions, which we see as the ELFs. Now, the other thing that can happen is when that charge imbalance happens, so we remove a certain amount of charge from the cloud, it creates a quasi-electrostatic field, so a DC field between the ionosphere and the cloud. And this field is enough to accelerate free electrons upwards, collisions, ionizations. Then we have sprites, and we have halos, and we have other things. The electric field in the tip of the lightning can be so strong in a very short distance, centimeters, to have a free electron in the atmosphere go as fast as 89% of the speed of light. When that happens, the cross-section of this particle becomes very small, and it starts to interact with matter in a different way, by Compton interaction, by Bremsstrahlung, and this process can create gamma rays, which is represented here. So the gamma rays are photons. They go up to outer space in a straight path. They are created in an isotropic manner. In their process of going up, they can interact with an atom, and they can create electron-positron pairs, which can help populate the lower radiation belts. So this whole range of phenomena are called FAIRIES. which are effects signaling the electrodynamic coupling between the atmosphere and space. That's an acronym that I created. I hope that the community embraces it the same way they embrace the word sprite. So we keep the fun in the field of research. So sprites are part of the transient luminous events, the plasmas. We have here a representation of sprites. This is a cartoon in correct vertical scale. So these are small sprites here, but they can go from 30 to about 100 and a little bit more kilometers altitude. There are the halos, they are diffuse plasma with diffuse optical emissions. They can be up to 100 kilometers in diameter. The ELFs can be up to 600 kilometers in diameter, so that's a lot. Here we have representation of blue jets. They leave the clouds as lightning and they change plasma regime as they go up. They can go up to 40 kilometers altitude, and the gigantic jets do the same, but up to 100. So they literally close the electric circuit between the cloud, which is in the troposphere, and the ionosphere. And the energetic part of the FAIRIES are the HEETs, the high energy emissions from thunderstorms. So we can have X-rays, gamma rays, neutrons, and electron-positron pairs. Now, I mentioned this is the newest component of the system. So we know as the energy of the sun comes into the Earth, it doesn't just create the magnetosphere and ionosphere, but all the interactions create what we call space weather that affect our communications, our navigation, and so many things in our modern coupling from below already for some time in the form of atmospheric waves. So that's mechanical coupling. They affect the ionosphere, create plasma bubbles, and many other effects. And now we have the FAIRIES, which are an electrodynamic component, which also can create these perturbations in the ionosphere and impact the inner magnetosphere. But we don't know yet how much is the impact. It's such a new area of research. Quantization is necessary, and it's an important aspect for future research in this field. So this is just to tease your interest. It's some work I started with some colleagues at INPE on what are the possible impacts in the ionosphere. So this is an ionogram, and as I play the movie here, you're gonna see some sporadic E-layers pointed by an arrow. Well, we were studying the ionosphere in days where there were sprites in that region. So we saw formation of sporadic E-layers. We were careful enough to choose days where we had low geomagnetic activity or moderate activity, so we could exclude the effect of magnetic storms. Those are just preliminary results. We need to go more deeply into it, but we started looking and seeing these things. And so sporadic E-layers and spread F we observed in those nights with the thunderstorms. This is not restricted to our planet. Many bodies in our solar system have atmospheres. Several of them have electricity. We know there is lightning in Jupiter, in Venus, in Saturn, and other bodies. And by effect, we have observed lightning in Jupiter. So this is a sequence of an optical flash of lightning discharge in Jupiter, seen by Cassini. And more recently, Juno, another NASA spacecraft, saw optical signatures in Jupiter of what may be TLEs, so sprites, halos, and ELFs. So 11 transients that match the characteristics of the transient luminous events in Jupiter. So are there FAIRIES in Jupiter? We don't know for sure, but there is a very strong indication that yes. So the optical component seems to have been identified. How about the energetic part? Does Jupiter emit gamma rays like the Earth or neutrons like the Earth? we need to make those measurements to establish that. We know that Venus also has lightning. The current estimate is that has half the lightning rates that Earth does. So could that be fairies in Venus as well? So this would be a very interesting topic of investigation. Just a very quick retrospective of how this research came about. So the first thing to be discovered was that the early fast VLF events are related to lightning. That was in '88 by Umar Inan and his group in University of Stanford. Then in '89, Franz and colleagues in Minnesota discovered Sprites. So what you see there is the very first image of Sprites. In '99, we found out that lightning can cause ionospheric heating, and that has been extensively studied. In '95, Sandman and colleagues from University of Alaska Fairbanks named Sprites, got the first color image of these events, the first spectra, did triangulation. They discovered blue jets. So here you see a temporal sequence of blue jets seen from 2 different airplanes. Again, this was a campaign funded by NASA. So there were flying airplanes around the thunderstorm, and they were able to do the triangulation and establish that they do happen in the mesosphere up to the bottom of the ionosphere. That's what really started this field of research. In '95, they went to South America. Those were the first observations of Sprites in South America over Peru on airplane. In '96, the Alps were discovered by Fukunishi, a colleague from Japan. In '99, Hans Nilsson and colleagues from University of Alaska, and I'm happy to say that I am part of the colleagues that made the first high-speed observations of Sprites. This is when I started my PhD in Fairbanks, and it was my very first field campaign, so it was really exciting. In 2001, there was a big discussion in a meeting at AGU. People were showing images of halos, which is what you see here, a halo with a sprite and a halo alone, and we're calling them ELFs. So that those are the very early days of this research area. And it was between a discussion with Barrington Lee and Jim Westcott in that conference that halos received that name, and it was established that they are different phenomena from ELFs. In 2002, we did the first ground campaign in South America, and we did the first sprite observations in South America from the ground and in Brazil in general. So these were the events that we saw. The first one was the first Sprites we saw in Brazil. And here we have the Sprite spectrum is measured by this campaign from Dave Sandman and colleagues. And the solid line here you see is the Sprite spectrum. The vertical lines are the aurora spectrum. So they match, and which means the physics that creates the aurora is the same physics that creates Sprites. The difference is for aurora, the electric fields are very high altitude, and for Sprites, they are established by thunderstorms. So it was from this comparison that Dave Sandman first proposed the generation mechanism of Sprites. Something interesting that we also did was to see, okay, if that is the physics, the electromagnetic radiation up to the ionosphere, for example, at that time using the HAARP project, are we going to see optical emissions similar to Sprites? And we tried that, and this is what you see here. So you see the image of a Sprite here in the mesosphere, and you see optical emissions excited in the F region. So it was a way to confirm this mechanism in those days. So I'm going to skip this because I already explained how the mechanism for sprites work. I want to show a little bit more detail here. So we can model this by our dipole, so the two charge centers in the thunderstorm that I mentioned. We can describe these charge centers. There are many ways of doing it, but this is the way I did in my PhD a long time ago. And we can solve Gauss law. We can solve the continuity equation. We can assume Ohm's law, and the electric field is minus the gradient of the potential. So we actually solve the Poisson equation that you see here for the thunderstorm charge source and for the charges that are induced in the atmosphere. And we can work with this modified version of the continuity equation that has explicit dependence on the atmospheric conductivity. And that is very important because the conductivity has an ion component and an electron component. Here we see the total conductivity of the atmosphere modeled, and the dots are data from rocket measurements. The ion component you see here, and the electron component we can model based on the electron density of the ionosphere using a Chapman function. And as you can see here, the electron conductivity depends on the electron charge, the electron density, and the electron mobility. Now, the density and the mobility, they do change when we have a change in the electric field. So it's a very complex function. As you see here, it's an empiric complex function of the electric field and the density on the ground and at altitude. We are not used to think that the electron mobility changes at all. We used to think that the electrons move with a certain constant way, but they don't. If we increase the electric field, this is what happens with the electron mobility. So this means that this is a self-consistent problem. You can solve it directly. You have to do iterations and take those things into account. The other factor is the electron density, which is also changing with the electric field. There is ionization and there is attachment. And this is also, there is also an empirical equation for that. And it's very counterintuitive because as you increase the electric field, the dominant process is attachment, so up to a certain point. So you are increasing the field, electrons are being lost, they're not being generated up to a certain threshold, which is what we call the electric breakdown threshold, which is this field, this line you see here. And from that point on, ionization dominates. So it's not very intuitive at all what's happening up there. And this all play a role on how these plasmas are created and also how the high energy components of the FAIRIES are created. This is the work of a former graduate student of mine. So he followed the model of our colleagues in Europe, Alejandro Lucchi and Uti Ebert, combined with this model that I did for my PhD. And it's very interesting to see that we have an ionization wave. Now, why is this showing this? Oh, okay, well, so there is this ionization wave that happens, and as this wave goes down in more dense atmosphere, it steepens, and from the center of the wave, a streamer can start. So it's, if we're going to study the details of the process, there is more that goes into it. And we see here this structure that I was mentioning. This is a high digital photography from a group of what we call column sprites because they look like columns. And you see the very fine tendril structure. These are all plasma streamers. If we zoom in the figure, we see those things have spatial scales of tens of meters. And these will have hundreds to kilometers. So there's a mixture of spatial scales here and different things that are happening in the temporal development of this phenomenon. You see here a group of sprites seen with a camera that has 30 frames per second, which is the regular speed that we use. Now, if you go to higher speeds, like this video here made by Hans Nilsson and colleagues from University of Alaska, 10,000 frames per second. If you notice, this is the correct vertical scale because they triangulated the event. You will see a phenomenon that seems to be completely different. You see the ionization wave going down, and then you see all the streamer discharges starting first down and then going upwards. It looks like fireworks. And we need very high speed imaging to resolve the whole microphysics that's going on in this phenomenon. Also, TLEs can change the chemical composition of the atmosphere. This is a model. There are three different models at the moment in the literature. One is from Sentman, again, showing that there is a production of many different species. You can see here the result in the sprite streamers. And the main component that's very interesting because it has an effect on climate is the production of nitric oxide. Nitric oxide participates of the chain of destruction of ozone. So around 70 kilometers, we have a lot of nitric oxide being produced during the summer. Somehow this mass of air can get down and off and measured here by this HALO satellite. This is a plume of nitric oxide from the central United States in the summer, going to west due to the winds at an altitude of about 35 kilometers, which is the altitude of the ozone layer. So FAIRIES can have an impact on weather and on climate by chemical reactions. So it's those phenomena that they are highly multidisciplinary. They connect with many different aspects of our system and our fields of expertise. Here I'm showing a very nice picture of a blue jet. So you can see a pretty image here. And the gigantic jet, which starts similar to the blue jet, as you can see, but it looks like a sprite on the top, is actually because it's spanning many orders of magnitude of density here, and the plasma regime changes completely as it approaches the ionosphere. We have in this image global distribution rates estimated in 2008 by colleagues in Taiwan who were responsible for the ISHO instrument on board the Formosat 2 satellite. So ISHO was looking at all the different types of TLEs and estimated 1 sprite per minute, 1 halo per minute, and 2 hour surprise 35 elves per minute. From the ground, the elves are not very visible. Their luminosity is very low, and it's mainly absorbed by the oxygen in the atmosphere. But if you're seeing from space, they are about 100 kilometers. There is not a lot of atmosphere going on the path between the satellite and the phenomena. So we discovered from satellite observations that they are the dominant type of TLE. And since they are in the bottom of the ionosphere, they make quite an impact on the ionospheric density, especially on the lower ionosphere above regions where there are thunderstorms and lightning. And you can see the global distribution here in this map of the lightning discharges. Then I want to switch a little bit to the energetic components. So the gamma rays are called terrestrial gamma ray flashes. They were discovered using, again, a NASA satellite, the Compton Gamma Ray Observatory. Colleague Fishman published a paper in Science with this discovery that the clouds on Earth are making gamma rays. That was astonishing for all of us. Then NASA RESI satellite came along, and the colleague David Smith made observations, studied this data, seeing that each location here, each cross is a location where RESI observed the gamma ray. And they estimated at that time, that was 10 years or more ago, 500 gamma rays per day on Earth. I'm sure if South America was included, we can see here no data was collected. And because of the South Atlantic anomaly, the magnetic anomaly, most scientific satellites shut down in that region. So that's an important reason to have the LEONA network right there. Here is the lightning distribution. We can see that if we expect this to be proportional to the lightning rates as we see in the other regions, there will be a lot of gamma ray emissions here in South America. So if we follow a thunderstorm from beginning to the end, I am sure that the rate will be much more than 500 per day. This is a very nice short movie. I don't know if it's going to play the sounds or not. We'll see. From NASA, astrophysics, about the discovery of positron emission from thunderstorms. So I'll let the movie speak for itself. No sound. Let's see if I share sound, if that will make any difference. If I try to share the sound. Is there an option to share sound in Teams, Jake?
Share speaker. Set the speaker.
Yeah, the speaker.
Yeah.
Unmute the speaker.
You turn yours.
That will create that.
So you're muted. I think you can turn your speakers on, but stay muted, and it should play.
But that's what I just did. Okay.
The owl may be picking it up. It's rewording. Yeah, the owl is the mic.
Okay, so we won't work.
But it will do the speaker too.
Speaker. Should do this. The owl is the speaker.
Yeah.
They have to change the setting. Go to the three dots. The three dots.
Yeah.
Go click it. Go system settings, settings right there. Purple. Yes, and then
Here?
device setting. And then check the speakers.
Here, show meeting details.
It says echo.
Yeah, so right now the owl is the speaker, but we want it to be her computer.
Okay, well, that's okay. Too much time on that.
Okay.
It would be cool to have the sound, but it will be without sound. So how do I share again? Here, right?
Yep.
So you're gonna have to read the caption, and I will talk a little bit through it, and oops. So there were some nice thunderstorm sound effects with this. Yes. So at any given moment, there is about 1,800 thunderstorms anywhere in the planet. And these observations from the Fermi telescope show that thunderstorms can make antimatter. The whole thing starts with a gamma ray flash. And the places, the dots are where Fermi has observed gamma rays around the world in the first 8 months of operation. The estimate is this about 500 TGFs a day, what I just said. And as Fermi was going over Egypt, it saw TGF from a thunderstorm that was outside its visibility range. So the big question is how that happened. How could it have detected it? So the idea is that with the intense electric field in the clouds, the electrons are accelerated upwards, as I mentioned before, and then they get near the speed of light. When they see an atom, they may interact and create a gamma ray by Bremsstrahlung emission. This gamma ray may interact with an atom and create an electron-positron pair. Since they are charged particles, they may become magnetized as they reach a certain altitude and follow a magnetic field line. So this is how they reached Fermi. Whichever magnetic field line Fermi was at, the cloud of positrons passed through and created gamma rays at the detector. So the detector was the source of the gamma rays because the interaction between antimatter and matter created photons. So it created gamma rays and it detected its own gamma rays. And since the phenomena repeated itself a few times, they could tell from the energy and the timing signature that they could be electrons and positrons. So that's how these observations with the Fermi telescope showed that the atmosphere can make antimatter. So I already mentioned in general how this happens. I just going to glaze through. This is the transport equation for electron and other species, and different things are taken into account. How the particles flow due to the electric field, how there is diffusion. This is the diffusion coefficient, which is a tensor. This needs to be taken into account for the movement of these electrons. And this is the term that talks about loss and gain due to avalanche multiplication for the electrons. And this is the source. So how these electrons and positrons are being created. And this is modeled using Monte Carlo simulation, which take into account the main interactions for runaway electrons, for positrons, from X-rays and gamma rays. So there is energy loss through ionization and atomic excitation, Bremsstrahlung and Molar scattering, electric scattering, Bremsstrahlung production of X-rays and gamma rays, the propagation of the photons, the absorption, Rayleigh scattering, Compton scattering, pair production, annihilation of positron and propagation, and the Baba scattering interaction for the positrons. So all of this go into the model. Is a very nice model. It explains most of the energy produced. However, when the Italian satellite Agili came and made measurements of TGFs, it saw photons with energy up to 100 MeV, which is a lot. Star supernovas, they have energies between 20 and 40 MeV. So we have something in the atmosphere creating photons with have energy equal to star explosions and more, and we don't explain that. The red line is the current model, and it does not fit this part of the spectrum. So there is a huge debate now in the community trying to understand how are these very energetic photons and then neutrons and positrons and everything else that they can create are being generated in our atmosphere. They may have an impact on our health. We don't know very well yet, especially for people flying airplanes because the atmosphere is thinner up there. This is the rate for mild radiation sickness, and this is the regulatory limit for TGFs, and we can see that their dose is higher than this. So those things need to be studied as well. What is the impact on our health? They are very fast, microseconds, milliseconds, but they are very energetic. Now switching to what we have done in South America, just a very brief overview. So in the beginning, we would go to the field, we would stay a month or two there and would have 1 or 2 nights of observations. And that's what you see here is a summary of these observations. Each color are TLEs in different places that we have observed both from the ground and on airplanes. You also see here where the tropics are, and you see where the magnetic anomaly is. So we're very fortunate down there, one way or another, because we have a magnetic anomaly on the top of us. For science, yes, but for life, the extra radiation, we don't know exactly what the impact it can be, right? So these are examples of sprites that we saw during these campaigns, and we studied the convective systems that create them. Above the tropics, we see tropical convection. Below, we see mesoscale systems very similar to what happened in the US. Here is the map showing the center of the anomaly. So this is the lowest intensity of the magnetic field of our planet right above South America. And this is where we started the LEONA Network because we wanted to study thunderstorms in different regions. We wanted to have an easier way to collect data than going to the field and spending so much time there. So we were able so far to install 8 stations in South America. So the dot is where we have a station. The red circle is our blind region. This is about 100 kilometers. We're looking at the limb. So if I have a cloud here in between me and the thunderstorm, it will block my view. So after 100 kilometers, most of the time, if there is a cloud, it won't be blocking, or it won't block completely the view of the upper atmosphere. The green circle is our estimated maximum range. You see that it changes from station to station. The only one that we know for sure is of this one here. This is the INPE observatory in the south of Brazil. This is about 1,100 kilometers, and we know that because we have estimated the location of TLEs as far as this line. So we cover very nicely this region. This is about 1/3 and to 1/2 of South America. We made several observations here. I have to say that LEONA is the Transient Luminous Event and Thunderstorm High Energy Emission Collaborative Network. So collaboration is an important component of this network. And to ensure that we have very good and healthy collaboration, we have a conduct code that is of no discrimination, no harassment of any type between the scientists, the students, and anybody, any institution participating on this network. So far, we have been very successful in making sure that all the interactions are in a positive way. Why installing a station in North America, and why the place I picked, which is an excellent facility, I have to say, of New Mexico Tech, the Langmuir Observatory. It's up in the mountain, 3,000 and some more meters. I'm proud to say that this was due to a contact of this former student of mine, Caetano da Silva, whose theory work I showed earlier. He is a professor there, just received tenure, so I'm very proud of him. And their excellent colleagues there, Richard Sonfeld, who is the director of the observatory. So we managed to do a very nice job installing the equipment up there. And the place of choice is because the general meteorology in large scale is similar to South America. So I will start here because you know this region better. So the main ingredients are warm, moist air, which here come from the south, from the Gulf of Mexico, through a low-level meteorological jet that gets coupled to a high-level jet that flies over the Rocky Mountains. And the coupling of the both creates like a vacuum cleaner effect, bringing the moist air up and creating very large thunderstorms with a lot of lightning and a lot of TLEs. So when I started my research in the University of Alaska, we would come down here to make the observations in the high plains. In South America, we have a similar effect, but the moist air comes from the Amazon forest. So all the transpiration of the forest, and that's yet another coupling with the forest and vegetation, creates this moist air that flows down with this low-level jet following the Andes Mountains. And the high-level jet gets coupled here and creates this explosive thunderstorms. We have an extra factor that is the polar air masses coming from the south that creates extra forcing. And here, this region has the Plata Basin, which has a lot of water. So the end result is that satellite studies show that that region in South America have the most severe thunderstorms in the world. So we have lots of lightning, we have very long lasting thunderstorm, very huge systems that probably create lots of FAIRIES. So this is why I started Leona here, because of the meteorological conditions, also because of the anomaly, magnetic anomaly, and then the North American station will allow us to make very nice comparisons of what we see in this region with what we see in this region and many more studies. So looking at Leona from a larger perspective, from a more global perspective, this is the green are the installed stations in South America. The yellow is our recent station, the coverage of our recent station in North America. We are looking for a second place, another observatory that we can have overlapped field of view to make triangulation measurements and also to be able to look above Langmuir Laboratory because they have a very nice and rich suite of equipment there for lightning studies, and it would be great to have TLEs on the upper atmosphere and the lightning measurements down below in the cloud. So the pink ones are places that I'm studying the possibility of installing new stations. This is a schematics of the network. So this is one site for the optical emissions. We also want to see the energetic components, and we have right now a neutron detector that is shown here. I had installed in Argentina for a campaign. And here you see a picture of me on the top of a high tower. Inside these cases are the nighttime cameras. We also have a daylight camera. We have this structure that's called a pentilt that rotates, and we can move the whole thing from home via internet. It goes through a central server at INPE headquarters, and anywhere in the world, we can make these observations through the internet. To the outdoors equipment, there is an indoors component that has a computer and other things to GPS timestamp the data. So the nice picture you saw of me there is on the top of this tower. This was a water tower in Argentina. You see, we have a very nice field of view here, except for the mountains. But this is the site that we have our best observations because we have very clear sky and very low light pollution in that place. This is a picture of our system pointing down because of the daylight. We want to preserve our camera, so we keep it down during the day, pointing towards the north. North is this way. Our sensitive cameras are in here, and this is, again, a daylight camera. So this is in Langmuir Laboratory in New Mexico. Here we have an example of a sprite here. So you see in real time, it's very fast. And here it's the event. So single sprite. That's the first event we saw with LEONA Network in 2018. And here you see a column sprite, similar to the beautiful colored images I showed before, but in black and white. So this is a column sprite here. Here you see in real time what we call dancing sprites, which is a sequence of sprite events. And here you see the same event in a narrower field of view in slow motion. So you see an event on the left first, and then the sequence in the middle. So this is an example of other events. So these events have been seen in different locations in South America. This is a halo with sprites. We see some structure in the halo. This is an ELF. The bottom of the ionosphere, we see only half of the ELF. We see striations here that are probably due to gravity waves. We published a paper with a colleague. He was studying gravity waves, and we saw sprites in the same night. So we have several of those. And to finalize, I want to show some images from a campaign we had last year from the ELEON-ES project, imaging of lightning and nighttime electrical phenomena from space. I'm part of this project. This is from my colleague in Israel, Yoav Yair from Reichman University. I'm part of the project, and besides that, we combined. So that was an astronaut that was up in the International Station making Sprite and other TLE observations. And besides that, we combined with ground measurements with LEONA Network in South America, trying to make simultaneous observation. We did not get simultaneous, but we got data. They got data, we got data. The astronaut got data, and we got data with LEONA. So what you see here are images of halos and elves. Here we see the donut shape seen by the astronaut. And that's what I wanted to show for today. The good news is that we're going to repeat this campaign this year at the end of May. So having a LEONA station in North America also increases our chances to make those simultaneous observations. Thank you.
Open this, this side too. Thank you very much. You're gonna check chat for people, but anybody in the room with comments? Yeah, Tom?
Yeah, you have the map of the state locations you were choosing for the LEONA network in South America and North America.
Yeah.
Magnetic equator goes kind of diagonal through that thing. I was wondering, is there a magnetic line connection between some of those locations by any chance, where something that,
No,
okay.
they don't.
Just
But
wondering whether there'd be an advantage to that,
And
stuff might propagate.
the magnetic equator has a dip and goes
Yeah,
like this. And
yeah, right through there. So the lines are a little catty corner through there.
Yeah, unfortunately for the southern stations, they are gonna be probably in this region. We do have magnetic conjugate points in Brazil,
Okay,
but we're not quite there yet.
okay.
We would like to have a larger cover
Yeah.
in the continent, step by step.
Okay, yeah, thank you.
Yeah, so clearly the kind of a thunderstorm activity is the primary driver for a lot of this. So what is the kind of the magnetospheric piece to this? Is there a modulation of these phenomena by the magnetospheric particle precipitation, the electric fields that they get imposed through the magnetospheric effects and so forth in terms of the Sprites and FAIRIES and all that?
The coupling coming from above will have an impact in terms of changing the conductivity in the mesosphere and in the bottom of the ionosphere. That will have an impact on how often the TLEs will happen, where they're going to start, but none of that has been studied yet. So we know that just from the general physics, but nobody has sat down to look at the data and to do these studies.
So you haven't seen like a solar cycle modulation or any of those?
No, because for solar cycle modulation, you have to have consistent measurement throughout at least 11 years. Yes, and we don't have that. So LEONA will have the capability of providing data for those studies. It's a single network, the same type of equipment, making measurements consistently. In 11 years, we'll be able to start studying these effects. But there are things that we could study more immediately. If we get the data from, let's say, magnetic storm and particle precipitation, we see how much it changed the conductivity, and we have TLEs happening in that region, we can see directly if there is an impact or not. If we don't have TLEs happening, we will know how the conductivity of the atmosphere looks like, and we can put that information in the models and see, okay, what kind of TLEs, what are the differences that we would expect to see due to that impact.
Yep,
Are there monitors in the rural regions because why I'm asking is that in the rural regions, there is a lot of modulation of conductivity
Yes.
by precipitation. So even if the rates of events are lower, if we were to monitor in those regions,
Mhm.
would we not be able to sort of pinpoint how coupling from above?
That's an excellent idea. The challenge is that the aurora oval is in a region where thunderstorms happen only in the summertime. And summertime, we have daylight most of the time. So those phenomena we observe at night. So the challenge is to make these observations. Having said that, there are very few, and I remember one observations of this type made in Europe, because then the oval is a little further south. It was somewhere in Scandinavia. I don't remember the name of the colleague, but he saw Sprites with aurora. But this is very rare, and this was a while ago. The idea of the coupling has been becoming more clear as time progresses, and as people like myself have been saying, yeah, we have coupling going on here. We need to look at that. So it would be great if we could, for example, revisit that publication, and if the colleagues have the data to see, okay, what was going on there in the electron density and etc. Thanks for the question.
Else? Okay, I'll ask a question. So I'm pondering the right place to put a station. It has to be a place where cold air meets warm, humid air, and you get big thunderstorms. So that's why you had a map of North America and stuff. Those are two places where that happens. It also should be a place where it's usually dry, so you have good visibility and not clouds all day and all night. But also you sometimes get thunderstorms off in the distance, so you can see. Is that the decision making? What?
Okay, so
How did you decide on the site you just put one? Why is that the right place?
okay, because let's Nicole.
Also with flatness of the terrain, so you can see a
Yeah,
long
maybe you want to
way.
be on a mountain looking at
Yeah,
a flat place. Yeah.
Mountains are always great because of the curvature of the earth. They give
Okay.
us even longer
Oh, you can see it with
visibility.
Yeah.
Yeah, so they're always great, but if they have other mountains around, then we have to weigh the cost benefit, which is what I did in Argentina. The one site I showed you, there was a mountain covering about 3 degrees in the horizon. So a very dry place is great because there will be very little rain at the place. So we have most of the year visibility, but it has to be looking at the place where, as you said, the hot, moist air meets some other kind of air that will be forcing for a thunderstorm. And here in the US, this is where it happens. And New Mexico is right here. Langmuir Observatory is somewhere in here, and it meets this criteria. They do have thunderstorms happening there during the summer, otherwise there will not be a lightning facility in the top of the mountain. But it's not that many. So it's a great place with good visibility to this region where there will be lots of thunderstorms. So the station, we don't want it in a place where the thunderstorms happen, but we want it in a place that will get great viewing of the upper atmosphere above the thunderstorm. Yes.
It seems like there might be citizen science potential for these observations. I don't think the cameras have to be that sophisticated, do they?
They don't. They do need to have a very high sensitivity to light. These cameras that I use in the LEONA network, they are the least sophisticated and the cheapest possible, which are still scientific data quality. But the main characteristics they have is that they are have very high sensitivity to light. They can see up to 10 to the -4 lux. So that's the main parameter. And yes, there is potential for citizen scientists. We had some citizens around the world who are excited because they're beautiful phenomena to see. They are taking measurements, and I have to say that we have a colleague here in Goddard who is Burcu Kozar.
She's online.
Yeah. Hello. So she created the first network of citizen project for Sprite and TLE observations, and that's going very well. So we have been communicating for a long time before I came here, before she did the network, and since I am here, we are both looking forward to a time that we can talk and see how we continue with our collaboration.
Yeah.
Yeah, I mean, can you go back to that radiation dose image you had? I know that seemed a little alarming, right? You know.
Yep, it is.
So you know, so you have the horizontal axis was a beam diameter. Could you elaborate a little bit? What is the how does the electron beam diameter connect to the kind of the dose level here?
Okay, so as you are away from the TGF, the beam diameter
This is
increases and the radiation dose goes down.
Yeah.
So the closer you are to the thunderstorm,
see.
to the source, the higher the dose you're going to get. Because the photons, once they're created, they propagate in a straight line and isotropically. Whichever direction they were initially created, that's how they're going to propagate. So the beam opens up with the distance.
So
is.
So is this modeled or actual observed?
This is modeled, and there are some observations of measurements on airplanes of the dose.
And it kind of agrees with the this.
I don't know. This is a very sensitive.
That's why I'm asking. Impressed by airline. Don't worry about the lighting.
Yeah, I mean, you know,
Flying over the pole in a thunderstorm, you're just doomed.
if by a single event, you immediately pass the regulatory limits. That could be
Yes.
pretty alarming.
It
story
is,
right there.
yes. So my colleagues started to study this, started to make measurements, but for some reason that research did not go very much forward. I think because it's a very sensitive subject. What I can say is that I remember David Smith, my colleague from University of California, the C is for what?
SC?
Santa Cruz?
Santa Cruz.
Yes, he had a project called Adele. He put sensors in an airplane. He flew near thunderstorms, but he couldn't get as near the thunderstorm as desired for the measurements. And he made some measurements. He reached some conclusions, but this is how it is at the moment. Maybe some other colleagues made some measurements as well, and I don't remember right now. This is the one that comes to mind. The point is there was some modeling, there were some measurements, and things stopped there. I think this is a very important thing to be investigated.
Yeah.
Not just in airplanes, but also on the ground. We are subject to this radiation, and not just gamma rays, neutrons, and whatever else is created. If a lightning strike a tree right there, and if the energy is enough, there will be a radiation dose coming to the building. If we're behind concrete walls, we'll have reasonable protection. But if we are exposed, we don't know how much radiation we're getting. Having said that, human species and all the biological
Yes,
systems,
right.
yes, because thunderstorms exist, the planet is here. But the thing is to think, okay, so if we have climate change, the temperature of the earth is increasing, thunderstorms are more in certain regions and others not. What happens to the people living in the regions where thunderstorm rate is increasing? And we already seen this in big cities that have a heat island effect. São Paulo in Brazil, for example, strong heat effect for the concrete, lots of lightning. What happens then? So we need to study those
I
things.
guess, another question related to this is that, so soon, we have, members of the community who have flown dosimeters on aircraft and various, kinds of platforms, NASA, research aircraft and also commercial aircraft.
Yes.
I know Ken Tobiska, is a good example from Space Environment Technologies, and he's been partnering with the airline industry for many, many years. And they've been flying his ARMAS package, which is kind of a miniaturized dosimeter. I don't know if that's, sufficient for capturing some of this, those elements. But I think that could be a really rich, observational data source to looking into this, because I know that they've flown that package on many, many flights over the years.
Yeah, that's very nice. Also some colleagues in Brazil do the same kind of investigation with dosimeters on airplanes. There are features, I don't know the specifications of the equipment, so I cannot tell, if it would be enough or not to see it. The TGFs, they are very fast. They last milliseconds, microseconds most of the time. And this equipment is measuring just a constant flux coming. That's much higher than the TGF itself, right? And that's of more concern at the moment than the TGF, because that's a constant source of radiation. TGFs are punctual things that are happening. So evaluating the effects, the proportional effect is something that needs to be done. I don't know if that dosimeter would see a TGF depending on the time resolution that it has. And it needs to be flying near thunderstorms. So if they're flying in very nice weather, they're not going to see any of this. So there's all of these elements to the equation that need to be considered.
Yep. I was wondering if you had a chance to look at the also X-ray and UV from that emission.
Personally, I have not, but there are colleagues who are looking into those things. We make the difference between X-rays and gamma rays from the energy of the photons, not necessarily from the physics that's going on into generating them. And so X-rays, if I remember correctly, is about 120 some kilo electron volts, according to the definition in this community, and gamma rays, everything above that. And if you're studying a photon that has 20 MeV, for sure, this is not from the electron interaction, but from the nucleus. So the physics follow the energy definition. So colleagues have measured X-rays from trigger lightning. Our colleague Joe Dwyer, who did most of the modeling, he has done this type of observation. Now, for the UV emission, that's a new thing. I can cite two examples. There is a suite of equipment on board the International Station called ASIM. It's an atmospheric and space interaction monitor. It's a European collaboration. They have different equipment. A colleague from Denmark called Thorsten Leibert. He's the PI of ASIM, of this mission. And they have seen UV emissions from ELVs from space. So we know that TLEs make UV radiation. Now, the other UV emission I was going to mention, yes, is in Argentina, there is the Auger Observatory for very high energy cosmic rays. And they have an array of UV detectors that work together. And a colleague from Europe, Roberto Musa, he coordinates this array of UV emissions detectors. So he has seen over Argentina ELVs and Sprites and other things in his UV detector, which was originally planned to see the UV emission from an energetic cosmic ray coming into the atmosphere. So we know they make UV.
Hey, anybody else?
Anybody in the chat? I don't know.
They have slowly dwindled, but at one time there were about 20
Okay,
people,
all right.
20 people there, including all the great names you would like to see joining.
Okay.
But it's being blocked by this. It's just,
But there's no question, is that a question from online? It is.
it's someone posted a link.
Okay,
Link.
all right,
Something to
so
look at.
I guess, thank you again for all the questions, for attending, and for this opportunity.
Yeah, thank you again.
Thank you.